Good morning, students. So, I am here again. So, on the last turn, we all studied about uniform circular motion, centripetal force, and centrifugal force. Okay? So, now, today we are going to take a fresh chapter. We are going to study work. What is work? What are the conditions? Different cases when we say that it is done and not done, and so on. So, we are about to study work. So, we move further. So, in normal language, what is work? Normally, we say that today I'm so tired. Since morning I'm studying. Or we say that since morning I'm teaching, not had a glass of water also. I'm so tired. Working since morning. The entire day we were working. Or if you have done cycling or you have done something else. So we say that we have done work. Any physical or mental thing which we do, we call it as work. But in physics, work is not any mental thing done. There is a definition for work in physics. And what is that? Work is said to be done only if there is a move in the object where force has been applied. That means if force has been applied on some object and that object displaces from its position, then we say that yes, work has been done. There is work. Work has been done. Okay. Now here in these pictures, we see that a man is pushing a box. A man is taking a box on an inclined plane. A boy is forcing a wall, and one more boy is pulling something towards himself. In the first case, where the man is applying force on the box and the box is moving, work is done. On the inclined plane, where the man is pushing the box on a slope, the box is moving, there also the work is done. In the third case, where the boy is pushing the wall is not being displaced. He is applying force, but the wall is not being displaced. Therefore, no work is done. And in the fourth one, where the boy is pulling the board towards himself and it is moving, yes, the work is done. So, whenever the force is applied on an object and the object displaces from its position, we say that work is done. Okay, so we studied that what is the definition of work in physics. That means whenever force is applied and the body displaces, the work is done. Now, in this slide, we are going to study that how is work measured. Okay, so the amount of work done by force is equal to the product of force and displacement of point of application of force in the direction of force. That means if the object is moving in the direction of force, then work is done. It is not necessary that always the body displaces in the direction of force. This is just a definition that the measurement of work is done as product of force into displacement, and displacement in the direction of force. Okay. Here we can see that the boy is pushing a box and the other boy is also helping to carry the box. Then there is a boy who is pushing a box and the boy is throwing a stone. Maybe somewhere the force applied is less, somewhere the force applied is more. Somebody is applying some other magnitude of force and somebody is applying some other magnitude of force. So it depends, and how much the body displaces. Okay, so it also depends upon some factors. So we are going to study this in the next one. Okay, so as I mentioned, the amount of work done depends on two factors. Now, what are these factors? I also mentioned the magnitude of force applied, and second, the displacement produced by force. So that means work is equal to F into S, where S is the displacement. So if S equal to 0, W equal to 0, when you are applying force and there is no displacement, then work has to be 0. So when direction of displacement of the body changes, work can be calculated in two ways. Whenever I said that if the work is done in the direction of the force, then it's okay. And if it is not in the direction of force, then we calculate it in the direction of force. How? By these two ways. When direction of displacement of the body changes, work can be calculated in two ways. Number one, by finding the component of displacement of body in the direction of force. And number two, by finding the component of force in the direction of displacement. So we change either of the thing. Either we make force in the direction of displacement, we find it out as components, or we find out displacement in the direction of force. Okay. So how to do this, we will learn in the next slide. Now students, what is component? If we don't understand what is component, then we will be unable to find out how is work calculated. Okay. So you all have studied right angle triangle and the trigonometrical ratios. Sine theta, cos theta, must have studied in class 9. Sine theta is equal to perpendicular upon hypotenuse and cos theta is equal to base upon hypotenuse. You have learned this. So we are going to use those trigonometrical ratios in the triangles which we form over here. Okay. So now here I have taken a triangle, the first one, where suppose A is, we assume if suppose displacement is in the direction of A here and force is applied in the direction of X. Okay. So in that way, how will you calculate? We have to find out the component in this direction. So how to find out the component? We are going to do that. Now suppose the angle made from the vertical component here is theta. Okay. Now, this is a right angle formed. I'm talking about the first case. So, please see clearly. Please take a copy and pen and sit. You have to calculate at some places because you have to be very clear with all this. Okay. So, here the angle theta is made from the vertical component. Okay. Now let us take that as AX and this as AY. That means the vertical component as AY and the horizontal component as AX. Okay. Now, this is A, this is theta. Now, cos theta will be, for cos theta, base will become AY. So, cos theta will be AY upon A. Whereas sin theta will be AX upon A, isn't it? So, AX it will be A sin theta. Cross multiply, A will go to that side. So, AX will become A sin theta. Similarly, AY will become A cos theta. That I have not shown because you can calculate that. Because if you take cos theta, it will be AY upon A. So, cos theta is equal to, AY is equal to A cos theta. That you can calculate. Now we come to the second triangle. Okay. Now if this is A and the vertical component here is AY and the horizontal component here is AX. In that case, and theta is the angle you can see. So in that case, cos theta, that is the base, the cos theta will be AX upon A. And when we cross multiply, it becomes AX is equal to A cos theta. Similarly, that side it will become AY is equal to A sin theta. So you know in what case it will be A cos theta and in what case it will be A sin theta. The base will become the hypotenuse into cos theta and the perpendicular will become hypotenuse into sin theta. Is that okay? So we move to the next slide. So, here we have taken the first case when we have to find out the component of displacement along the force. Okay, so we will make displacement in the direction of force. Now we have studied that work is equal to force into displacement. Now, just look at this triangle. That box has been moving on that inclined plane and force is being applied in the horizontal direction. You can see that, and displacement is inclined. So we have to make displacement also in horizontal. Now, if this is F and displacement is taken as S and this is angle theta being made, so AB, that is the base, will become hypotenuse into cos theta, as I mentioned earlier. So, displacement in the direction of force will become S cos theta. So, we come to the formula W is equal to F into S. Cos theta, I have shown how to calculate. So, AB is equal to S cos theta, we have calculated. So, W is equal to F into S cos theta. So, W is equal to Fs cos theta. Okay. Now we learn how to find out the other component. So we move further. So here, finding the component of force along the displacement. Now displacement is in this direction only. We are making force in the direction of displacement. Okay. Now how to find out the same formula, W is equal to F into S. Okay. Now look at the figure properly. The triangle is there, displacement S is there, theta is between S and AB. The triangle is ABC. You can see F is in the horizontal direction. There has been made one more triangle. Can you see that? And PN is the normal drawn. From when the displacement is extended back, PN is the normal drawn from the line where F is there, from that line. Okay, you can see that. Now, theta and theta will be equal because it becomes vertically opposite angle over here. Now, in the smaller triangle, you can see that AN, if you see, that will become the base and F will become the hypotenuse. So, AN will become F cos theta as according to the condition which we studied of components. So AN becomes F cos theta, and F cos theta is in the direction of displacement, and displacement is S. So we apply the formula W is equal to F into S. Now, when W is equal to F into S, in place of F, we have to write F cos theta, because it will be in the direction of displacement and displacement is S. So W again becomes Fs cos theta. So whatever way we take, the result is the same. In that also we got Fs cos theta, and in this also we got Fs cos theta. So the formula of calculation of work will be Fs cos theta. Okay. So we move further. Now there are some special cases with work. And what are these? The first case is when the displacement is in the direction of force. The first thing which we studied, the displacement in the direction of force. In that case, cos theta will be 0. There is no angle between force and displacement. That will be 0, and cos 0 value is 1. That means work will be maximum. When displacement is in the direction of force, cos theta becomes 1, and therefore work is equal to W into S, and that is the maximum work done. For example, if a ball is falling freely from above towards the ground, okay, now it is moving towards the gravity, the force is being applied down, and displacement is also towards the ground, and so both are in the same direction, and so this will be taken as maximum work. Okay. Now in the second example, you can see that the man is picking up the box. So displacement is against the ground, above. Displacement is above, and force is being applied also above. So both are in the same direction, and therefore work done is maximum. Okay. So we move to the next case. Now, okay, so second case is when the work done is 0. And this will be when either the displacement is 0, when there is no displacement, work done is 0. And the second case is when the displacement is in the perpendicular direction to the force applied. In that case, cos theta becomes 90 degree and cos 90 is 0. So work done will be 0. If you can see, this man is taking this load on his head and is moving horizontally. So force is being applied in upward direction and displacement is horizontal. So that is perpendicular to each other, and therefore work done is 0. Similarly, we studied about centripetal force when a body moves in a circular path in a horizontal plane. No work is done since the force on the body is directed towards the center of the circle. The displacement is along the tangent and the force is towards the center. So tangent and radius are perpendicular to each other in that case, and therefore the work done is 0. So we move to the next case. So here the third case is when the work done is negative. So when force is in one direction and displacement is in another direction, the angle between force and displacement is 180 degree. In that case, the work done will be negative. As in this example, you can see force is being applied towards right and friction is towards left. So displacement, you can see pushing force is towards that side and friction is towards this side. So it is a different direction, and therefore in this case work done will be negative. Okay, so if the displacement is in the direction opposite to that of force, then theta will become 180 degree and cos 180 degree is -1, and therefore the work will be negative. Okay, so we move to the next slide. Okay, so here this is for when work done by the force is in the form of gravity. So work done will be the same thing, F into D. So F is mg, you know. Work done, force can be mg also. Ma, mg, acceleration due to gravity, mg, and displacement is h. So when it is for the gravity, then work done will be mgh. So formula applied will be mgh. Now the units of work, you know, it is force into displacement. So unit of work, for force it will be Newton and for displacement it will be meter. So Newton meter or Joule, SI unit, Joule. CGS unit, it will be dyne into centimeter. Okay, dyne is the CGS unit of force and centimeter is CGS unit of displacement. So dyne into centimeter, which is ergs. Now relationship between joule and erg, 1 joule is equal to 1 Newton into 1 meter, and 1 Newton we know that it is 10 to the power 5 dyne and 1 meter is 100 centimeter. So 1 joule is equal to 10 to the power 5 dyne into 10 to the power 2 centimeter, and that is 1 joule is equal to 10 to the power 7 ergs. Now I could have given some numericals to do, but I want power also to be done, and then only I'll give you some numericals. For time being, I am giving you some work. Try to do it on your own, and if you have some problem, please do tell. So till then, take care. Bye-bye.